Welcome to Catalyst Education. This video is about mass spectrometry. The mass spectrometry is an analytical technique. This is used for many high-tech purposes. In this video, I want to discuss how to find out different isomers of organic molecules using the technique mass spectrometry. The device mass spectrometry has 4 different stages: ionization, acceleration, deflection, and detection. The sample be changed to vapor. One or more electrons are removed from molecules to produce positive ions. An ion accelerating electric field with plates with slits form a narrow beam. A magnetic field deflects the ion beam. The ion with the greatest mass and the smallest charge is deflected the least. Ions hit a detection plate, producing a tiny electrical current is applied. The more ions of the specific mass is to charge ratio, the greater the current and the taller the peak. Fragmentation pattern in the mass spectra of organic compounds. When the vaporous organic sample passes into the ionization chamber, a mass spectrometer, it is bombarded by a stream of electrons. These electrons have high enough energy to knock an electron off of an organic molecule to form a positive ion. This ion is called molecular ion or sometimes the parent ion. The ion is often given by the symbol M+. Fragmentation. The molecular ions are energetically unstable and some of them will break up into smaller pieces. The simplest case is that a molecular ion breaks into 2 parts, one of which is another positive ion and the another an uncharged free radical. Simplified mass spectrum of pentane. If I see here, it has 5 carbon and 12 hydrogen, so the MR is 72. At 72 we are getting the parent molecular ion. Another fragment is 57, that is deducting 72 from 15, CH3. CH3 is the free radical. Another peak is the 43. It has the highest one. It has highest abundance, so it has more stability. And the last one is 29, is for C3CH2. The mass spectrum of pentane 3,1. And here the MR is 86. At 86 we are getting the parent molecular ion, and for 57, that is C3CH2CO. For this we are getting a positive ion. This fragment has the highest abundance, and the 29 for CH3CH2. Peak heights and the stability of ions. The more stable an ion is, the more likely it is to form. The more of a particular sort of an ion that's formed, the higher its peak height will be. The order of stability of carbonate ion: primary, secondary, tertiary. Tertiary has the highest stability and primary has the least stability. Simplified mass spectrum of 2-methyl-butane. Here 43 has the highest abundance. This is from CH3 CH3 for the secondary carbocation, and the parent molecular ion is 72. For the greatest stability of secondary carbocation, we are getting here the highest abundance. Using mass spectrum to distinguish 2 compounds, we are giving here 2 isomers of pentane 2,1 and pentane 3,1. If we see here 43 for pentane 2,1, CH3 and CO. For this cation, 43 has the highest abundance, but pentane 3,1 we are getting CH3 CH2CO. 57 is the highest relative abundance. The mass spectra of M+1 peak. This is associated with carbon 13 isotope. The ratio of M and M+1, when given, we can find number of carbon atom in an organic molecule. And so the ratio between these two is 1.11% of M+. The relation is here: M plus divided by m plus 1 is equal to 100 divided by 1.11 multiplied by n. Using we can find the number of carbon atoms in the organic molecule. If we give here an example, m and m plus 1, the ratio is 43.3 and 3.35. From this ratio, we can find the number of carbon atom in the organic compound L. 43.3 divided by 3.35 equal to 100 divided by 1.1 multiplied by n. The n is 7. So the L compound has 7 carbon atoms. Here, the ratio of m and m plus 1. From this, we can find out the mass spectra of M plus 2 peak. The M plus 2 peak is related to chlorine or bromine atom present in the organic molecule. If the ratio of M and M plus 2 is 3:1 chlorine atom is present, if the ratio is 1:1 bromine atom is present. If we see here example 2 chloropropane chlorine atom is present. So here the M plus is 78 taking chlorine 35. And when we're taking 37 of chlorine isotope, we're getting M plus 2 at 80. From this ratio, M plus and M plus 2 is 3:1, so chlorine atom is present. This is the formula. Two chlorine atoms present in an organic compound. 1,2-dichloroethane. Two chlorine atoms are present. If we take here, chlorine is 35. The M plus at 98. One chlorine is 35, another is 30. 7, we're getting m plus 2 is at 100 mass charge ratio, and the last one 102 for the both chlorine atoms 37. So the ratio is here 9:6:1. From this ratio we can call it 2 chlorine atoms are present in the organic molecule. The simplified mass spectrum of bromoethane, if I see here, the ratio of m and m plus 2 is 1:1. So here the bromine atom is present. Again, we are getting the example here m and m plus 2, 43.3 and 14.1. So here, explain what element is indicated by the m plus 2 peak. Here the ratio is 3:1 of 43.3 and 14.1. So chlorine atom is present. Three methods of dating using mass spectrometry: carbon dating, potassium argon dating, oxygen isotopic ratios in the dating of I score. Carbon dating used the radioactive isotope of carbon-14 in the dating of once living artifacts is well known, but because of its fairly short half-life, 5,730 years, it becomes less accurate for ages greater than about 10,000 years. Potassium argon dating, naturally occurring potassium contains 0.01167% of the radioactive isotope of potassium-40 with a half-life of 1.3 to 9 years. So if an igneous rock sample contains the potassium and the argon formed by the decay of potassium-40 is unable to diffuse out of the crystal lattice, so it is possible to determine the age of the rock sample. Organic isotopic ratios in the dating of I score, naturally occurring oxygen consists of three isotopes: oxygen 16, 17 and 18 in the percentage abundance 99.76, 0.04 and 0.02 respectively. Most of the ice in the ice sheets and the O's has been formed over the many thousands of years by water molecules evaporating from the oceans and traveling in the vapor state towards the polar regions. The use of combined ZLC and MS in environmental monitoring. Biomarkers in the petrochemical industry detecting PCBs and the dioxin and the Mars Viking landers. Two stories of detecting with mass spectrometry, the solving of historical mystery and ecological detective story. Thank you very much for watching this video.